So I'm going to be on page 9. Page 9 is where we're going to be. Cool. All right. I'm going to jump into Desmos and kind of do an example. And it's either going to crash or burn, but hey, let's try it anyhow. So, my friends, let's say I had a quiz out of 20 points. Actually, let's do a quiz out of 10 points. And these are the following scores.
I'm really upset over Ryan that I had a crush on him. Ryan, still very long. I like how you don't know who she is, but she's your whole ex.
Yeah. Oh my God. I have no
Anyway, I'm still so upset over her card. I've never said that. I didn't know. And why did it spread so far too? Like I had another person come to me and tell me,
All right. All right, so what I have here is, looks like I have 60 or a whole bunch of test results. Let's say I gave a quiz to a certain class. It wasn't this class because we can't use our own data because that'd be goofy. But let's say I had a quiz that I had given every year that I taught CP Algebra 1. Being I've taught CP Algebra 1 for 24 of my 26 years teaching, I have a whole lot of data, and I always give the same quiz. Okay? You following me in this adventure? So let's say I have my data and histogram of X1. All right. So this is fictitious data of a 10-point quiz that I've given my entire career. This is an awful lot of data. This is a histogram to represent the scores of my data. So what kind of curve does this kind of look like? What do you kind of notice about this? What is it? Oh, close by is right. But it's called bimodal. Bimodal. Okay, so friends, this graph is bimodal, meaning does this look like a normal distribution? No, normal distribution should look like a bell curve, right? Sorry, I interrupted. So let's say we have this kind of data. This created a bimodal piece of data. Okay? So as I add more and more data to this, let's say it's even more and more bimodal as we have collected the data on it. Okay? So bimodal is not a normal distribution. Agreed? And I realize I have like 60 or 70 pieces of data in there. But so if I show all, it's an incredible long piece of data. Okay? These are just scores that I just fictitiously made up, but just pretended that they exist. So we have bimodal. So does everyone feel comfortable that this is not a normal distribution? Does this make sense? Okay. So we're set. Everyone's happy with that. If I had this on a test saying, does this appear to be a normal distribution, you would be able to say no, because there are two peaks. It's bimodal. It doesn't look like a normal curve. It doesn't have the shape of a bell, something like that. You could tell me that. Agree? Okay, so on page 9, So that's what we're starting with that. So on page 9, we're going to start looking at something called the central limit theorem. So you remember with data that we were talking about, you have a population mean, and then you have a population standard deviation. And then you can change that and start saying, well, I have a sample mean. And the sample mean and the population mean are going to remain the same. But the sample standard deviation is going to change to, oh, I'm so sorry. It's going to change to, we can call it the standard error, we can call it. So we talked about this, and the standard error basically comes out with being the population standard deviation divided by the square root of the number of things, number of people, number of items, okay, of our test. Okay, so what basically happens is the standard error, so the standard deviation is kind of spread out. As I start increasing the size of n, my standard error, which is replacing my standard deviation, is going to approach closer and closer and closer and closer to what the mean would be. Does that make sense? So if I did on Desmos, oops, go back to Desmos. If I did on Desmos, if I got rid of my data, and I got rid of my histogram, and if I just did a standard normal distribution, oops, normal distribution, and if I had, say, a mean of 65 and a standard deviation of 7, and if I wanted to look at what this normal distribution looks like, this is going to create our normal distribution. And we can start finding the probabilities. Like if this was a final exam, and we could say, hey, if I picked one person randomly, what's the chance I would pick somebody who would score a 67 or higher? And in this case, it would be a 38.8% chance. Okay. Now, if I went and changed my went from my normal distribution with my entire population, and I changed it to my standard error. So then if I said, well, I'm going to change this, I'm going to say, well, we're going to divide by the square root of, let's say we picked 50 test items. So then you could say, okay, so now what's the chance that I pick 50 people randomly that they would score better than a 65%? And in this case, it goes to roughly a 2.1 probability. Okay? So because I am changing the denominator, yes, I am taking the square root of the denominator, which you found in Algebra 1 was a big no-no because you didn't want to have that take place. What happens is I start squeezing together the standard deviation. The standard deviation is going to become the standard error. They kind of work, standard deviation is entire population. Standard error, when I'm selecting a certain amount of people, I'm going to get closer and closer and closer. I'm approaching what the mean would be. So it's getting harder and harder and harder to deviate away from that with the standard error. Okay, does that make sense?
So is this what you put in the calculator to find the standard error?
Yeah, the standard error is, the nice thing is the standard error is really easy on Desmos to plug in, because you could just change whatever your standard deviation is, just go divided by square root of how many people you're picking.
Okay, so you don't have to actually
Mm-mm.
Okay.
And that's a real huge benefit of Desmos. Okay. So those are a few things taking place. Now, if I had my data and it's skewed right, or if it's skewed left, or even if it looks kind of strange like this, if this is my entire population of what it has done, if I use the central limit theorem, if I pick greater than or equal to 30 people, and statisticians have proven this over and over and over again. So it means you're going to select 30 people or more, or 30 items or more. The central limit theorem is going to allow something that is not a normal distribution to become your sample approaches being a normal distribution. Okay? This is going to allow our goofy graphs to approach a normal distribution, meaning it'll make it closer to look like that. Okay. Now, what's a word that is up there that has some wiggle room on it? What's a word up there that has some wiggle room? Let me highlight it for you in case you can't figure it out. Approach. So does it mean that if I were to select greater than 30 people, I have a normal distribution? So be careful how this wording is. It's going to approach a normal distribution. So does that mean if I had a whole population, I have all my ACT scores, and let's say my ACT scores were not normally distributed. They are skewed right or left, or they have a couple of humps in there, or whatever. If I randomly select 30 or more individuals and try and figure out their data, I am going to approach a normal distribution. I'm not going to get to a normal distribution, but I'm going to approach it. And if I approach it, then I can start using my normal data features. Okay? So if I had some, oh, I don't want that. I want to have a pen. If I had something that's skew right, it is really horrible statistics for you to then start applying our statistics tests to our normal our not normal distribution. Unfortunately, it happens. Okay, so what's basically happened here, if you remember back in the day, if it's skew right, that means that the mean is to the right of the median. If it's skew left, then my mean is to the left of the median. The median is the middle data. But if I can't use normal stats tests on something that is not a normal distribution. But if I say I have a not normal distribution for my entire population, I'm now going to select 30 or more things. So let's say I am canning, let's say I work for Coca-Cola, and you have the 12-ounce cans of Coca-Cola. Okay, and that Coca-Cola, those cans are going through the canning plant, and those cans are being filled with really close to 12 ounces of Coca-Cola. But let's say you run, I don't know, 1 million cans of Coca-Cola through the thing, and the district manager comes walking in the plant and goes, I understand that we have a huge problem. We're telling people here's 12 ounces of Coca-Cola in this can, but there's some weird statistician out there at Cherry Creek High School named Chris Stirrup who says he's not getting 12 ounces of Coca-Cola. So what we're going to do is we're going to take all 1 million of these cans. A million cans is a lot of cans of Coca-Cola, agree? But what we're going to do is we are going to open each and every one of those cans of Coca-Cola, and we're going to measure the volume of how much Coca-Cola is actually in each one of those cans. And let's say we find that we are actually skewed to the right, meaning Chris Stirrup is claiming I'm not getting enough Coca-Cola. They're saying, well, shoot, it's skewed to the right, so our average is higher than our median, so it's skewed right. So, friends at Coca-Cola, it looks like we're actually selling more than 12 ounces in our can. That's fitting because there's a little bit of wiggle room in those cans for a little bit extra volume to go into. So then that manager is going to go to their actuarial scientists, which are statisticians, and say, hey, this guy's making an awful lot of noise. He went to 9 News. So we're on the news now. How are we going to defend this on the news? Because the news is knocking at our door going, hey, Chris Stirrup, he's kind of a big deal. In his own mind, but it's kind of a big deal. Follow me in this adventure? He's claiming that we're gypping him. We say we're giving him 12 ounces. He's claiming he's not getting 12 ounces. He drinks Coca-Cola all day long, and he's a sick enough individual that he pours the entire volume of every one of his cans that he has cracked open into a device that shows the volume of what's coming out of the can, and he's claiming it's not. We're showing that we're actually giving more because we just selected an entire population of 1 million cans of Coca-Cola. Okay, so let's say we know it's skew right. Let's say that Coca-Cola, after 1 million cans, is showing that it's skewed to the right, meaning the manufacturer is claiming that that each one of their cans has greater than 12 ounces of Coca-Cola. And then the statistician's going to say, whoa, wait, project manager, hold your horses. You're showing that you don't have a normal distribution. You have something that's skew right. Correct. So the Coca-Cola guy's going, all right, we got this. Chris Stirrup has no idea what he's talking about. We're right, he's wrong. So let's say Coca-Cola is finding that they have, of their 1 million cans, they are showing a 12.1 ounce average of those 1 million cans. Okay, 1 million cans of Coca-Cola, a lot of Coca-Cola. Does everyone feel comfortable with that? And I know you're thinking, okay, this is kind of crazy, Stirrup. Why in the heck would Coca-Cola worry about emptying 1 million cans of Coca-Cola to check the volume of each one of those? They don't want to get sued. It's not costing Coca-Cola a lot of money because Chris Stirrup, this dude right here, I'm pushing a lawsuit against Coca-Cola for misrepresenting their cans of Coke, 12-ounce cans of Coca-Cola is not 12 ounce, and I'm going to sue Coca-Cola for $20 million. Okay? And this is just fictitious. I'm just making this up, but I'm just saying. I have now created an enormous lawsuit against Coca-Cola. Now, $20 million against Coca-Cola. Coca-Cola could handle a $20 million lawsuit. But Coca-Cola is also going to realize this. They're going to say, hey, time out. This dude wants $20 million. So they're going to get all of their real smart people and their attorneys together saying, does this guy have a case? And the lawyer's like, yeah, we might want to just cut this dude a check for $20 million and he goes away. And so that's what the attorneys are saying. Okay, then he goes over to the statistician and says, hey, how much is this going to cost us if we test to see if this village idiot in Greenwood Village, Chris Stirrup, that he has a case against us? And so the people who are number crunchers are over there and they're like, well, it's going to cost us $100,000 to prove or disprove this guy's claim. So the people of Coca-Cola, the president and the CEOs and CFOs and all the people that are in charge of Coca-Cola are like, okay, so is it worth it to us to spend the $100,000 to try and disprove this stirrup character, or should we pay out $20 million? Okay, so think about it. If you were working in a corporate office and you're looking at a $20 million lawsuit and it's going to cost you $100,000 to verify if I'm right or wrong, would you as a company go and spend $100,000? Or are you willing to give up 20 million bucks? Bless you. So basically, Coca-Cola is now going to roll the dice on this. They're going to say, all right, we either pay Chris Stirrup $20 million or we do a test. It's going to cost us $100,000 to do the test. So we could either be out $20 million, $100,000, or we could be out $100,000, and that guy gets nothing. He's got to keep teaching. He can't retire on us. Okay? So think about what that company's choices are. And I think as a company, they would probably choose to say, you know what, we're going to fight this. You know, this guy has no idea what he's talking about. They're going to try and discredit me. Now, I'm going against a big corporation. That's pretty tough. I don't have the multi-billions dollars a year that Coca-Cola has. I have my nest egg. Am I willing to invest my nest egg to try and disprove? Am I willing to go and drop $100,000 to show that McDonald's or Coca-Cola is wrong? So it becomes a big tug of war. So now Coca-Cola says, okay, this is what we're going to do. What we need is we're going to go ahead and we're going to can 4 million cans of Coca-Cola that are going to sit there. And what we're going to do is we're going to have all those cans of Coca-Cola just sitting on the floor of the warehouse before we put them on pallets. So they got 4 million cans of Coca-Cola sitting on the ground. And then the statisticians are like, you know what we're going to do? We are going to select more than 30 of these cans at random. Okay? So they're going to sit there and create a random number generator saying, hey, we want to pick a certain amount of cans of Coca-Cola at random. And you got some poor soul that has to go and figure out where these cans are going to fit. And so the new guy that just came into the courtroom or the office room that we're working on, he's working on his PhD in statistics and says, hey, there's something called the central limit theorem in which we only have to select 30 or more cans of Coca-Cola, and we can show that we have a approaching normal distribution. So the managers of Coca-Cola, the CEOs are like, you say 30 or more cans? Yeah, so how many cans should we select? Well, it works if you choose 30 or more. So should we do 1 million cans? Well, no, sir. No. If you choose 30 or more cans, 30 to whatever number you want, but 30 is the baseline. So Coca-Cola says, okay. We're going to go get 30 random cans of Coca-Cola. We're going to take those 30 cans of Coca-Cola and we're going to take them over to our laboratory where those guys know how to read a beaker. And we're going to pour all of the each Coca-Cola, can of Coca-Cola, into this beaker, and they're going to tell us what we're going to have. And so now, let's say they had a mean of this, and they showed a standard deviation of 0.2 was what the original million cans had shown. Okay? So now we're going to figure out the standard error. And the standard error means I'm going to take the standard deviation, the 0.2, and I'm going to do this over the square root of 30. So now we're going to sit there and say, is this stirrup character in Greenwood Village at Cherry Creek High School has been teaching math for too long? Is he right or wrong? Do we have to pay out his millions that he wants? He wants 20 million bucks. This guy's crazy. So we're going to jump back to Desmo. So I'm going to go 12.1. 12.1, comma, and then I'm going to go 30. Oh, no, not 30. What was our standard deviation? 0.2, I said? 0.2 divided by the square root of 30. Okay. So if I go to my normal distribution, I go to this. I'm going to change this number. So what Coca-Cola is going to do is they selected these 30 cans. Still with me? So everyone feel comfortable? My standard deviation is squeezing in a lot closer. So now all Coca-Cola has to do is this. What's the probability that somebody of these 30 cans that we have 12 ounces or more are amongst our selection? So they have a 99.7% chance that if you selected 30 cans of Coca-Cola or more, or if it becomes more, it's going to get even bigger, and we're going to show. So Coca-Cola is like, wow. So if I selected 30 cans of those 4 million cans sitting there at random, we have a 99.7% chance that there are 12 or more ounces. And then they ask the legal people, what does the can say? 12 fluid ounces. So we have a 99.7% chance that we're going to get 12 fluid ounces or more in each can. So based on this so far, do I have a case? Am I retiring? I mean, because Coca-Cola would also do this. They're like, oh, okay. Hey, so that worked with 30. Well, what happens if we change that to 50? Now the probability that I select 50 cans. So I go take my standard deviation that was given from my whole population. I'm going to take by the square root of 50. And now they're going to say, well, shoot, if we select 50 cans, we have a 99.98% chance that any given can of soda is going to have 12 or more fluid ounces in it. And Coca-Cola says, we're going to take this one step further. They're going to prove this in a court of law. We're going to select 250 of those cans. If we select 250 of the cans, we have a 100% probability that if 250 cans are selected, that our average is going to be above 12 ounces. This stirrup character, he has no chance. He can't win. Okay? Now, they come back, Coca-Cola comes to me and says, this is what our data shows. Now, I, as the consumer that is trying to win $20 million from Coca-Cola, I might choose to do my own test. Here's where it's going to get costly. Friends, do you think I'm going to go buy myself 4 million cans of Coke to make this test? I don't have the money to do it. I can't prove it. My selection of each can of Coke I drink each day that I measure because I'm a geek has nothing to do with the production levels of Coca-Cola. So I took basically a skew right model, and I can't trust a skew right model, but I can start trusting a skew right model by turning it with a standard error into an approaching normal distribution. And now my statistics are going to work. Okay? So that's basically the central limit theorem. Now there is a disclaimer on page 9. It says, be careful, applying normal distribution techniques to a distribution that is not normally distributed is a huge red flag. Okay? But because of the central limit theorem, I can take something that is not a normal distribution and I can make it approach normal distribution by applying the standard error. Does that make sense? And I think that's going to help you. Now, the big key on the central limit theorem, your sample size that you select has to be 30 or larger. If it's less than that, there's a different statistical test that we're going to learn later in the year. But as of right now, we have to have 30 or more items in order for us to say, yes, this is approaching a normal distribution, or no, it's not. Okay? Does that make sense? All right. Now, words that you're looking for in your reading of the problems. If it already says it's a normal distribution, the central limit theorem's out the window. We don't have to worry about it. If it says it's not a normal distribution, then you have to apply and get the standard error by taking the standard deviation of the population divided by the number of items, the square root of the number of items you're doing. So, for next time, my friends, would you work on page 77, 78? See how you do. And sorry, friends, I didn't get to retire. It didn't happen.